Hi students, today's topic is network theorems. Network theorems. So far you would have studied various methods to solve an electrical circuit. We started with Ohm's law. We then saw in Kirchhoff's voltage law and Kirchhoff's current law. We used mesh analysis, nodal analysis. All these methods gave you the same answer for a particular circuit, but the only difference is the method of solving. And we do require these methods in order to make the circuit simpler. For example, if I'm using a mesh analysis, I have used this because this particular circuit will be it's very complex when you apply KVL and KCL or the Ohm's law in order to find the values of voltage or current. Similarly, nodal analysis also is one of the methods where you can find the node voltages through which you can able to find the currents. The difference between the mesh analysis and the nodal analysis are it's very simple. I give you a practical example that I will show you a circuit and I will tell you how it is different and why we have to which one we have to select and why. For example, you have a circuit something like this. So you have the resistors connected series and parallelly. So this is the circuit here. So we have various resistors, that is R1, R2, R3, R4, R5 and R6 or something like this, given with an input. They are asking you to find the currents through any resistor or voltage across any resistor. You can go by any of these laws. Either you can use directly only the Ohm's law or Kirchhoff's laws, or you can use the mesh analysis, nodal analysis, any one of those. But the selection of which method that I am going to use is more important, to which I will end up with the right answer very soon. For example, if I give this problem to a person who solves through mesh analysis, the another person solves through a nodal analysis, both gets the same answer, but it depends on how which method to be selected. So on looking at this, most of the people will think about going for the mesh analysis, so that you can apply mesh analysis where they will find 3 loops here. So they will end up with a matrix. Their matrix is R matrix in a 3 by 3 matrix. They will solve that. Hope you know how the process goes. Sometimes it is also easy for you people to solve it by nodal analysis, because in the nodal analysis we have only two nodes, one is A and B, and where we will end up with an resistors or the conductance matrix, that is 1 by R matrix of 2 by 2. So solving, there is a difference in solving 2 by 2 matrix and a 3 by 3 matrix. Whichever you feel is easy, this 2 by 2 will be a very easy matrix to solve. But also there are some certain restrictions when you select about this, because you need to check the type of voltage, what type of the sources that is given to you. In case you are going for a nodal analysis, you are supposed to convert, if it's possible you could convert the voltage source to a current source, then you can jump it. So it's between your choice. So similarly, the method that you use, it depends upon your flexibility or the easiness on the circuit, whichever you can go. Network theorems, coming to this chapter, network theorems are very important because they deal about the major applications in the real time. So certain theorems are applied on the circuit in order to find the exact values of the voltage and current that is required for the load. For example, in this network theorem we are going to see three types of theorems as per on your syllabus. The one is Thevenin's theorem, the other one is maximum power transfer theorem. The last one is superposition theorem. There are still 4 more theorems, but I am concentrating on these 3 theorems as per your syllabus that is given. Right, there are some reason that why you learn these 3 theorems. They are related to the real-time applications. In short, I would now tell you what are you going to see in these theorems, so that it will be very easy when I teach you the theorems in detail. So the Thevenin's theorem, you will end up with a value called as open voltage value, open voltage, or you call it as open circuit voltage, called as VOC, open circuit voltage. This open circuit voltage is the maximum voltage across any terminal. So in Thevenin theorem, you would find the open circuit voltage across any load. So this verifies that a particular terminal where the load has to be connected should have the maximum or the actual voltage that is required. For example, in our home, we are using a 230 volt supply. We are using a 230 volt AC supply, which is of 50 hertz. The place where the voltages or the power is generated will be of different values, but at any point, for example, you assume in this way, this is the place where the power is generated. This may be generated, this is a power station, and I would say, like, from here the power is distributed wherever it is required, to homes, to industries or commercial buildings or any residential buildings. It will be, so this is a load 1, load 2, load 3, load 4 and load 5. These loads are not much bothered about the power generation, about the values of power which is generated. These are customers. The 1 to 5 loads are called as customers. They require the exact power they want. Their demand has to be known by the power stations which generate the power. So for example, if I take the load which is 1, which connects to a home, which requires 230 volt 50 hertz AC supply, and I would say the fifth load is an industrial load which is requiring of 3.3 kV 50 hertz AC supply. It all means that the components or the appliances that is going to be used inside or in these loads depend upon a common voltage value. That is, for the first load, 230 volt is the common voltage that will be required for all the applications which is used inside this load, and 3.3 kV and 3.3 kV is the voltage which is required for the various appliances or the components or the loads which is used in the fifth feeder. So it is mandatory for someone who, when they design these power station or the load distributions, they need to decide or they need to confirm whether the terminals, the load terminals, I mean to say, this point is the load terminal for the first one, this is for the second one, this is third, fourth and the fifth, and all the voltage that is a load terminals should confirm that the minimum voltage of requirement is satisfied. That is, at this point there should be 230 volt, and at this point it should be 3.3 kilovolt. All these things should be confirmed. Only then the load, the components which is used for the home in particularly, there are many appliances like fan, light, air conditioning system or refrigerator, or any kitchen appliances. Okay, all these things are operated at 230 watt, right? So for a design to be done for the particular load system, we need to confirm the voltage that is available is the actual rated value of the voltage for each and every appliances. So in this case, Thevenin theorem is the theorem used to find the open circuit voltage at the particular load terminal, right? Similarly, the maximum power transfer is nothing but, by the name you can see that maximum power is being transferred. For example, for the same thing, if suppose the input power for this, I'll take it only for this load or this feeder which is feeding a home. So the input power is something, I take it as PIN, input power. And when this input power is fed to the loads, various loads like fan, light and refrigerator and everything, the output power is calculated, which can be of P naught. We all know from the formula of efficiency, usually given by like this, it's nothing but the output by input. In terms of electrical, it is output power by input power. So the output power which is in the numerator, mathematically you can see that how far this numerator is greater, the efficiency would be greater. For a very efficient theoretical analysis, 100% efficiency states that the input power and the output power are same, that is, our input power is equal to the output power. But practically this is not possible, because there is an energy transfer. For example, this is an electrical system providing an electrical input, which in turn is converted to a mechanical output. In this case of fan, it is converted into a light in case of, that is an light in case of a bulb, or it is converted to some other like a cooling system. Here also a cooling system, and depends. So there is an energy transfer from the input to the output. So whenever there is an energy transfer, there will be some losses. It is given as the input power will be equal to the output power plus the lost power, or they called as losses. So these losses are never be zero practically, but our need is to make these losses as small as possible, small as possible. So in that case, when this becomes smaller, the output power will be more, at least close the value of input power. By example, if I have the input power is of some value 100, there is a difference of being like this, 80 plus 20 or 20 plus 80. In this first case, we could see the loss is about 20 for from of 100. But in the second case, the loss is 80. So which is the least loss or the lower losses we get is the first case. So in order, even the better cases will be like having 95 plus 5, which means I am decreasing my losses to losses very far. So as much as possible I decrease the losses, the output power increases. So when the output power increases, the efficiency increases. So in order to have a transfer of power which of maximum, that is maximum power to be transferred, we have certain rules, or we have certain procedure to find it. So in order to check whether the provided circuit, the given circuit, is able to transfer the maximum power from the input to the output, we have to confirm that. So to make sure the power substation to work efficiently, I need to design a circuit which can transfer the maximum power from the input to the output. This is the ultimate thing. I cannot just simply design a circuit or design a load or give a connection to a home or any other industry without knowing how much power is being transferred. In case if the efficiency is very less, then whatever I do in the power station, whatever the power is goes to the losses. I'll be in loss. It means that if I am able to, that is, if my load requirement at the feeder or to the load requirement is about 20 kilowatts of power is required at the output. If my losses are high, that is, if I say my losses are about 50 percentage of losses, I should here be able to generate almost 40 kilowatts in order to supply the 20 kilowatts hour, because my losses are high. So in order to, you take it in this way, in order to feed 20 kilowatts of power, I am forced to generate 40 kilowatts of power. So it means by losses by losses almost 20 kilowatts of power is lost, right? That is only 50% is converted, the other 50% is lost, which is not an efficient system. But rather, if I design my system that is able to feed 20 kilowatts of power by generating just 21 kilowatts of power, I could efficiently say my losses is like 1 kilowatt. This is comparatively very less to the first case, but still going on in a very efficient way of producing the powers. If I am able to provide almost 20.5 kilowatts of power in order to feed my 20 kilowatts of power, my loss is just 0.5 kilowatts, that is 500 watts of power is wasted in transferring 20 kilowatts of power to the load. So this is how I have to think. So in that case, in the maximum power transfer theorem, we will study about the circuit, how it should be designed to provide or to consume the maximum power from the input. So that is all about maximum power transfer. Superposition theorem is a simple method of solving the circuits. Suppose you have more than one source of different type. That is, a circuit having a bigger circuit. Maybe you can take a bigger circuit which has more than one source, maybe 3 sources or 5 sources or more than that of different sources, like one being the voltage source, others being the current source, or the combination of this. It is very difficult to understand how to solve the problem or how to find it. In superposition theorem, what we do is we split the circuit. For example, if there is a circuit, if I would say this is the network, this network is given with some more than one source. Maybe for this example I'm going to take, there are 3 sources here, and that is, here I have 2 voltage sources, V1, V2, and 1 current source, and this being the network. This in the problem I'm asking you to find some value of voltage or current in particular part. So this, by superposition theorem, this can be split into 3 circuits, each having only one source. That is, I'm going to consider only one source for the first one. I'm going to consider only this network. For this first network, I'm going to consider only the voltage source V1. For the second I'm going to consider only the current source, leaving other circuit. And in the third case, I'm going to consider the second voltage source, here V2, leaving the other. So finding the net value of this will give you the combined value, will give you the actual the voltage or current which is asked to you. So this is the superposition theorem. So in superposition theorem, you supposed to split the circuit depending upon the number of sources given to you. If there are 3 sources, you will have 3 more circuits, that is, you will split into 3 circuits. You will find the voltage or the current whichever asked to you, and later on that will be found, the net value will be found, so that you can equate saying that the total, that is the change, the value of voltage or the current because of all the 3 sources is this. So you can do it. So with this we will now go in deep with these each three theorems, that I think that will be helpful for you to understand. Welcome back. So we start with the first theorem, which is Thevenin theorem. So in Thevenin theorem, so the statement, you should be very known to this statement of the Thevenin theorem. Later on I will explain you what it does it mean. So first we come to the statement. It states that the for any linear electrical network containing only voltage source or current source, or both voltage and current source can be replaced at the load terminals by an equivalent circuit having the Thevenin voltage and Thevenin resistance in series, right? So this is the statement of the Thevenin theorem. So they mean to say, like in any linear electrical circuit, so it means linear, the word term linear means it has to satisfy the Ohm's law. So actually Ohm's law does not satisfy in a non-linear electrical circuit. Only in linear circuit Ohm's law is satisfied. So thereby we can also verify the we can put the Thevenin theorem only in the linear circuits. So there is a linear electrical circuit which can contain voltage sources or the current sources, or both voltage and current sources, and that circuit can be replaced by an equivalent voltage and the equivalent resistance at the load terminals. To be much more clear, I can explain you with the circuit. So for example, I have a network which can contain any combination of resistance or even inductors and capacitors. I am given with an voltage source, a DC voltage source, which is taken as input voltage, and this is the load terminal. I can mark it as A and B as the load terminal, and the load is nothing but the resistance which is connected. So any resistance which is connected across the load terminals is taken as the load resistance, and the network will have any combination of resistance inside, resistance or any other passive components like resistor, inductor and capacitor, so on. So considering a DC circuit, I am involving only the resistance inside. So this this circuit can be replaced, or can be replaced by an equivalent circuit which will have an equivalent voltage source, which is named as Thevenin equivalent voltage, which is VTH, and a Thevenin equivalent resistance, which is RTH, which across the load terminal A and B. So here I will have another resistance which is called as the load resistance, and this could be the load current which is flowing through it, and here also load current. So any circuit like this will be fine. So it is very much clear that there are two important parameters to be found. One is RTH, the other one is VTH. So in RTH, RTH is nothing but the equivalent resistance or the equivalent Thevenin resistance of the network, leaving the leaving the load resistance. Without the without using the load resistance, we will calculate the Thevenin equivalent circuit for the network. And VTH is nothing but the voltage drop across the load terminal when the load is not there. There is the open voltage terminals. So I would further explain you in this way. Your VTH is nothing but is calculated by using this circuit, like a network circuit, which is we are having an input voltage here, and VTH is the measure of the voltage across the load terminal A and B. Okay, you understand? This is the VTH. So we will use this circuit to find the VTH value, and in order to find the RTH value, we will use the same circuit where you will consider only the network elements and the equivalent resistance RTH, Thevenin equivalent resistance, will be found of which is nothing but the equivalent resistance of the network is the equivalent Thevenin resistance. We will not consider the load resistance in that case. Alright, so it is very simple. So we will solve a small problem, or we'll take it as a we will solve a small problem so that you can understand how the Thevenin equivalent circuits are found. Right. So the first problem in the Thevenin equivalent circuit: find the load current IL for the given circuit using Thevenin's theorem. Okay, this is the question, and the diagram for the question is something like this. Right, so this is we'll have 100 volt, this is 5 ohms, 10 ohms, 10 ohm, and this is 5 ohm, and we are marking these terminals as the load terminal. So the problem is given like this. Okay, we need to find the load current. It is nothing but the current which is flowing through this load, which is this load current IL. They are asking you to find the value of IL. Okay, so this is the question given as with the diagram. So this is how it will be given. So they have said we need to find the load current. So always in the problem, the load will be either given by any terminals marked as A and B. Any terminal which is marked as A and B is considered to be the load terminals, and the resistance which is connected to that terminal is taken as the load resistance. So of course the current flowing through that branch is taken as the load current. At some cases what they do is they don't actually mean they say they find the current flowing through a 5 ohm resistance using Thevenin theorem. So in that case, the 5 ohm resistance is taken as the load resistance, and the terminal which connects the 5 ohm resistance is taken as the load terminals. And in that case, if they specifically say a particular value of the resistance, you will not have, or you will not have a repeated value of the resistance in any of the circuit, right? So in this circuit we are here to find now the Thevenin equivalent circuit. They haven't said about the Thevenin equivalent circuit. They are asked you to find only the load voltages, but however, in order to complete the problem, we need to find the Thevenin equivalent circuit from which we will find the load current. So coming to the solution, we are here to consider, that is, we'll write it as a statement: the Thevenin equivalent circuit is given as. So for the given particular circuit, the Thevenin equivalent circuit can be given as. So let me copy this. Sorry. Okay, let me copy this and I paste it here. Right. So for this circuit, we need to draw. We need to draw the Thevenin equivalent circuit. Let's see how it is done. The Thevenin equivalent circuit will be something like this. We'll have a very simple circuit. The Thevenin equivalent circuit is common for all the circuits, looks the same. Okay, so this is the Thevenin equivalent circuit, where this is the voltage which called as the Thevenin equivalent voltage VTH, and this is the Thevenin equivalent resistance RTH, and these two terminals are A and B, where you have the load resistance something like this, which is RL. In this case it is 5 ohm, and the current in this is given as IL. And from this diagram we can write the equation for the load current IL is equal to by Ohm's law. It's very clear. It's voltage divided by the total resistance. So here the voltage is VTH divided by the total resistance. Here you can find RTH and RL are in series, so we'll take it as RTH plus RL. So from this circuit we will be able to obtain the final value. So from here it is very obvious that we need to know what is the value of VTH and RTH, and in that case RL is known to us, right? So let us now find the step by step. We will see the step by step procedure to find the VTH and RTH. So first let me find the RTH value to find Thevenin's equivalent resistance. Okay, we are going to find this. So for this, coming to this Thevenin equivalent circuit, we need to know some basics on the electrical circuits in order to find out. The first thing in the Thevenin equivalent circuit, if you want to find the resistance in it, you need to remove all these sources. That is, you want to zero all the sources. It means the equivalent resistance, equivalent resistance is found without the sources. So in an electrical circuit, I will say some of the important note that you can note it down, that whenever you are going to make a source 0, it means the source, that is the value, is not available. In that case, an voltage source is made 0 by short circuiting, and a current source is made 0, that is the current is made 0 by open circuiting. Okay, so whenever you want to make a voltage source 0, you will short circuit the terminal, and whenever you want to make a current source 0, you will open circuit the terminals. So this is the important thing that you have to understand in any case. So similarly in this case, here we are going to find the equivalent resistance. So equivalent was a resistance. We will write it at the equivalent resistance across the load terminal A and AB is found by open circuiting the load. This is mandatory for any case. You have to open circuit the load, and we could clearly see in this circuit we have a voltage source. So in order to make the voltage source 0, we have to short circuit it, and short circuiting the voltage source, short circuiting the voltage source. So we will redraw this circuit such that we will short circuit the voltage source and open circuit the terminals. So I will copy it, alright. So what I do is, here I will short circuit this. So I have short circuited this, and I will open circuit my load. So this is where I open circuited. So this is the terminal A and this is terminal B. So I am ready now to find RTH along this at this terminal. So it is necessary whenever you calculate the RTH, that is the equivalent resistance across any terminal, you need to solve it from its opposite side. So from here we will be solving, we will consider two resistance, which is this is 5 ohm resistance and the two is 10 ohm resistance. These two are in parallel. These two are in parallel, and the parallel equivalent value of this 5 and 10 will be in series with the 10 ohm resistance, that is this 10 ohm resistance. So it is very clear, we can directly write the formula in order to solve it. That is 5 is in parallel to the 10 ohm resistance, and in turn that is in series with this 10 ohm resistance, right? So in the formula we will be, let us substitute and find the answer. 5 into 10 divided by 5 plus 10 plus 10. So when you calculate this, you will obtain the value as 13.33 ohms, which is the RTH value. So from this we are able to find the RTH value as 13.33 ohms. Got it? So this is RTH, calculation of RTH. Now we will calculate the second step, which is called as the to find the Thevenin voltage. So now let's find the Thevenin voltage. To find Thevenin's voltage, that is VTH, across the load terminal. Since we are going to find the voltage across the load terminal, we can't make the input voltage 0 because we need that. So the voltage is measured across the load terminal for the given voltage in the circuit. The only thing what we do is we will remove the load and we will put a voltmeter. Practically what we do is we will remove this load, open circuit the terminal, and we will put a voltage across the terminals so that it can be found, or that is voltmeter across this terminal. So the equivalent circuit, or the circuit for which we have to going to find the VTH, is something we will remove this load. Okay, so something it will look like this, and now we are going to find the VTH value at this terminal point. So by electrically we will know that when a current, that is when the circuit is turned on, it means that the A and B is nothing but an open circuited terminal. And so when we consider the circuit, when the supply is on, that is 100-volt supply is on, the current comes out of here. This is the main current which comes out of here. It goes through the 5 ohm resistance is the first, and then at this point called as a node, and cannot be called as a node, but at this point what happens, the current will, like, tries to split up, but what could we see is like this 10 ohm resistance. This 10 ohm resistance is open circuited, that is, it does not have the other end of the 10 ohm resistance is not connected, it is just left open. It means that the circuit is open in this case, that the circuit is not closed. So we know that the current will always flow through only the closed area, closed circuit path, and if there is no path which is closed, it cannot flow through it. So the current, what happens, automatically flows through, the current has to flow, only in this direction, that is, it cannot take the other direction, it will go along this 10 ohm resistance, it cannot go here. So the whichever the highlighted and the red, the current in this branch, the current cannot flow because it is open circuited. So in this case the current, so in order to find the voltage, we know that we can find the voltage in as current into resistance, current into the total resistance or equivalent resistance, we say. This is the formula by Ohm's law. So in this case we could see the current coming out of this source will go through the 5 ohm resistance and then flow along the 10 ohm resistance, and this is the closed path, only closed path which is available for the current to move. So in this case we have only the 5 ohm and 10 ohm resistance where the current can flow. So these two resistance in this circuit, leaving out the other in the right hand side, is seem to have a series resistance. So eventually when you calculate this, that is, I want to know the current which is actually flowing through this, right? So in order to find the current, so other than this, so the VTH, which is nothing but, so voltage drop across the A and B terminal, it can be either that or it is nothing but the voltage drop across this 10 ohm resistance. Okay, voltage drop across the 10 ohm resistance. So this is, or more equivalently, the voltage drop across the 10 ohm resistance. So the voltage drop across the 10 ohm resistance is nothing but, I would remove this and I will give you this 10 ohm resistance is nothing but the by Ohm's law we will write it at the current through the 10 ohm resistance into the 10 ohm resistance is the voltage drop across this. So you need to find the current in the 10 ohm resistance. The current in the 10 ohm resistance is nothing but the same current which flows in the 5 ohm resistance, so because the current is going to be the same, which is nothing but the total current. So here the I, we know that I 10 ohm resistance is equal to the total resistance, that is, sorry, total current. So that is equal to by Ohm's law, it is voltage divided by the total resistance Req. So here the voltage is 100 and R equivalent is nothing but 15. So from this we can calculate that is current flowing through the 10 ohm resistance, or the total current is nothing but, the current is given as 6.667 or 6.67 amperes. 6.67 amperes. So this is the current flowing through that. So it is now very easy to now to find, which is nothing but 6.67 into 10, which gives you 66.7 volt. So this is the voltage across the 10 ohm resistance or the Thevenin equivalent resistance. So the Thevenin equivalent resistance is 66.7 volt. Now we have the value of Thevenin equivalent voltage and Thevenin resistance. Now it is very easy to obtain the equivalent circuit, which is this. I copy it Okay, this is it. So let us write a statement for that. Therefore, the Thevenin's equivalent circuit is given as this one. So we will replace all the values here. Okay, the value of the voltage is 66.7 volt. The resistance is 13.33 ohms, and we have this. So from here, therefore, hence the load current, which is IL, is given as the total voltage we are here is VTH divided by RTH plus RL, right? It is nothing but 66.7 divided by 13.33 plus the 5 ohm. So this is the value. So as we calculate this, we will get the value 3.63 amperes. So this is the current, that is the load current that was found for the given circuit by the Thevenin theorem. So whenever the question is asked to you, you should make sure that what is asked in the final thing. Either they have asked you to find the equivalent circuit alone, or they have asked you to find the load current. At times they would give you the circuit which has only the load terminals but no load. They will keep it open. For that cases, you will be asked only to find the equivalent circuit. So please read the questions properly and then you can answer it properly. And in cases they may ask you to find the power in that load, power in the exactly load. So if you want to find the power, so power can be found as the current square into the particular resistance which is asked to you. So this is the power dissipated in the load. So if it is asked, you can find it, else that is not required. So I hope you can understand this. Thank you. So welcome back. Now we will see what is maximum power transfer theorem. So we understood in Thevenin theorems that we would able to find the open voltage across the load terminals. And before in the introduction I was discussing about the maximum power transfer theorem. That is, this theorem is required in order to find how much of power can be, that is we need to determine the maximum power that can be transferred. So I told you why. I will quickly tell you why these things are more important, because whenever I consider a system, that is, if I have a generating station, it generates some voltage, and that is given to another network. The generation is taking place in this network, and then finally it is given to some load. Okay, this load can be anything like a fan load or a light load or anything that converts an energy. So there is an energy transfer is taking place, that is between these two. We can divide this into two areas. One is, this is the input side and this is the output side, or this input side is called as the generating side. Okay, and this is the utilization, where the power is utilized or converted, energy is getting transferred in this, right? So here this electrical energy is converted to another energy. That depends upon the type of load. If suppose it is a fan, it could be a mechanical energy. If it is a light, it would be a light energy. It is something else. Okay, so the electrical energy is being converted to some sort of, there is an energy transfer. So whenever there is an energy transfer, there should be some losses. That is the law of energy conservation. So the power which is measured here is taken as P in, and the power which is obtained here is P out. This is the output power. So input power is an electrical power, output power is some form of another type of others. And this by that equation of the energy transfer, we could say that the input power will be equal to the output power plus the losses. This is what we discussed before, and these losses are nothing but is caused because of the energy transfer, which cannot be zero practically. So it means that whenever there is an energy transfer, there will be some losses, but our design will have an importance on making these losses as less as possible, because in terms of efficiency, if I say my efficiency is calculated with the output power divided by the input power. So I should always have my the numerator greater in order to have a greater efficiency. In case if I have my P out equal to P in, my efficiency would become, that is 1, or in terms of percentage it is 100%. This is theoretically we can tell that we have 100% efficiency, but practically we will not have, because the efficiency cannot be 100. The reason is we will have some losses. So in case we reduce the losses, we will have the maximum efficiency. So because the output power can also be given as input power minus losses from the very first equation. So if the input power is 100, if I have as less as possible, if suppose I have my losses as 0.5, they will have my output will be a 95 point, sorry, this 99.5, we will have about very less value, which is 99.5. okay. So this is the reason why should I always have my output, that is the losses, very less. So it always deals about something, that is your power is getting transferred. So the maximum power is to be transferred, means we should have a less loss. Now this maximum power transfer theorem states, or it helps us to design a circuit which can transfer the maximum power. There is a certain condition. So as we look on this statement of saying the maximum power, if you look on this, you can clearly understand. The statement states that the power, or we can say this maximum power can be delivered to the load when the load resistance equals the source resistance or network resistance. So this is how it is stated. That means in any linear circuit, if the maximum power has to be delivered to the load, it can be done only when the load resistance equals the network resistance. So here we would say that the load resistance RL should be equal to the Thevenin equivalent resistance of that given network. So this is the condition for the maximum. So I will say that this is the condition for maximum power transfer. So in the questions they will give you a simple circuit, they will ask you to find the maximum power, and also they will ask you to find the load at which the maximum power is transferred. So this is the question that would be given to you. In that case, the formula for the maximum power is given as P maximum is equal to, it is VTH square divided by 4 RTH. Either it is 4 RTH, or we can also say VTH square is equal to 4 RL, because we know that RTH and RL are same. So in maximum power transfer theorem, a simple circuit will be given. They would ask you to find the load resistance. That is, the load resistance will not be given in the question. They will ask you to find the load resistance. That load resistance is found using the Thevenin equivalent circuit, the same procedure as we saw in the Thevenin theorem. Okay, we will find RTH. So that two steps which is required to find is the first step is very simple, that is you need to find the RTH value. That is, I'll write it in a simple way. First one, find RTH as same as the procedure in Thevenin's theorem. The second one, find maximum power using the formula known. Okay, so you should be very much known to this formula. You should know this formula and the condition. Okay, now we will see a simple problem. We will repeat the same question what was given to us in the previous, that is Thevenin theorem. We saw the problem. So let's see the same problem for which we will so take the problem. Find the value of load resistance for the given circuit to transfer the maximum power. Also calculate the value of maximum power transferred. Okay, I'll give you the circuit diagram. Well, let's take the same circuit diagram what we used in before. So this is the circuit diagram, the same circuit diagram. Only difference is we don't know the value of RL. Okay, so in this problem we need to find the value of RL for which the maximum power transfer can be, that is maximum power will be transferred. So it's very simple. If you are able to find the RTH value for the given network, this network, the equivalent value of this will be the same value of this. This is the condition for the maximum power to be transferred. So in the last case we can follow the same procedure. In the last case we found the RTH value by open circuiting the load side and short circuiting here. So we had 5 being parallel to the 10 ohm resistance, and finally the next 10 ohm resistance was in series. In that case we had 50 divided by 15 which gave you 13.33 ohms RTH value. So in this problem we will do the same procedure. So we found the value, the earlier value we will be able to get. So we would be writing only the statement as therefore the value of the load resistance for which the maximum power can be transferred is what? Equal to RTH. Therefore your RL should be equal to RTH, that should be equal to 13.33 ohms. So this is the first thing what we have found. The later they will be asking, they have asked you to find the maximum power, that is P maximum divided by that the formula is VTH square divided by 4 into RL or RTH. So in this case we should also know to find what is VTH. So since this is the same problem, in the last problem we had the value of VTH is 66.7. I am going to take the same value 66.7 divided by square divided by 4. RL value is 13.33. So let us calculate this. So when I calculate this, I get a value 83.43 watts. So this is the maximum power that I was able to transfer from my input to the output. Okay, so in order to verify this, that is my P maximum value is, that is the maximum power is 83.43 watts. I say now for the given circuit, this is the maximum power can be transferred. So in the earlier case with the Thevenin theorem, we found our the load voltage, that is the voltage value was VTH value was 66.7 volt. For the load value of RL was given as 5 ohms in the earlier problem, and the current was given as, so the current we found it as 3.63 amperes. This is the load current. So suppose if I want to find the output power, P out is equal to I square, that is IL square into R, which is equal to 3.63 the whole square into 5. So if I find it, I get it 65.88 watts. This is my output power for the previous question. So by which if I keep changing my value of load resistance, I would be able to get different power values, but in that I can infer that the maximum value of the power can be obtained only when my RL value will is equal to RTH. That is, my R value that can be equal only when this RL value is equal to 13.3 ohms. Only at this case, any value, the power will be very less, or wherever will be less or less than, that is less than 83.43 for any value of RL except 13.33. Either if you increase the value when C or you decrease the value. Let us increase the value when C, that is RL. We let us found the P outside, P out for a load value of we'll consider a new row RL value of 20 ohms. What is the power? Let us consider the power. So in order to find the power, I need to find a new value of load current, because in the earlier problem I found the IL for respect to this. IL was equal to VTH divided by RTH plus RL value. So VTH was 66.7 and RTH was 13.3. It is 13.33, sorry. Plus let us take the RL, new RL value as 20. I get a value which is almost equal to 2. It's almost equal to 2.08 something, approximately equal to 2 watts. So the power which is transferred is will depend, that is you need to have an exact value close to that value of RTH, that is exact value of RTH, only then the maximum power can be transferred, right? So this is how the maximum power transfer theorem can be inferred. So in order to find the maximum power transfer theorem, you need to follow the same procedure of Thevenin theorem. You need to find RTH and VTH, and from which the only thing is condition is for the maximum power to be transferred, the value of RL, that is the load resistance, should be equal to RTH, and the other values, that is your by finding the VTH value you will be able to find the maximum power that can be transferred, right? Thank you. I hope you would have understood this. So welcome back. The next one is the superposition theorem. So superposition theorem is one method of solving the circuits. It is not like a Thevenin equivalent circuit or a maximum power transfer theorem, which can be directly applied to a practical thing. This is a simple way of solving a bigger circuit which has n number of sources. So we can able to solve any value of voltage or current in the network or in the circuit by any method. But if the circuit is still bigger, and we still feel it's complex to solve in a basic way of solving, the superposition theorem can be easily applied, and this superposition theorem will be useful for you to in determining various that is various concepts apply that same theorem can be applied in any concept of the electrical networks in any in the thing what you study in the later cases. So in superposition theorem, the statement is a very clear statement as the superposition states that any circuit, that is any linear circuit, I'll write it, any linear circuit with multiple voltage and current sources is equal to the sum of simplified circuit using just one of the sources. This is a simple statement for the superposition theorem. So as I told you very beginning that the circuits can be solved in different methods, but in case the complexity of the circuit increases where you cannot proceed the other methods to be followed, we can use the superposition theorem, which will be easy for that. So in diagrammatically, if I have to represent it, if I have a network and there is a load connected to it, this is the RL, okay, and let the current IL is the load current, and we do know the voltage drop across the resistance is taken as the load voltage, the voltage drop across the load against, okay. So this is the network circuit, and this network circuit is given with many sources. This is source 1, this is source 2, source 3, and so on up to n number of sources. So that could be any combination, either it can be voltage sources, current sources, or the combination of it. If that is given to you, if you are asked to find any of this, load current or load voltage, we will be able to find in this way, where this circuit can be replaced by the sum of, okay, the sum of the circuit considering only one source at a time. That is the same network with the same, we need to find, maybe I take I dash and this is VL dash. We are going to find using only one source at a time. This plus the second time I am going to use this again the same circuit, again I am going to use the same circuit, but for a next load we will consider the second load in this case, second source in this case, and we will find the new voltage which is obtained because of the second source. Similarly, we will find for n number of sources, we will find for n number of sources, okay. Then finally we will add it. In case we need to find the current, we will add all the individual currents which is obtained from each sources. Summation of all these things will be give the exact value of this. So this is how we have to solve. So if you have three sources, we have to split it into three circuits. We will find the voltage or the current whichever is asked to you in three times, that is using each and every sources different times, and then we will find the cumulative answer for it. So now let us do a problem so that we will be able to understand very clearly the first problem in the superposition theorem. Obtain the current through 10 ohm resistance using superposition theorem. So they have clearly given you need to find the current through the 10 ohm resistance using superposition theorem. So you have to follow the superposition theorem, that the circuit will be like this. Okay, for this circuit they are asking you to find the current through this 10 ohm resistance. So the 10 ohm resistance is somewhere here, so they are asking you to find which goes the current which is going in this 10 ohm resistance. Okay, let me take this as the load current, and you are given with the sources here. Let us take this as 50 and this is 10 amperes, right? And so many people will think like you have given with the 10 amperes current source in this, so the 10 ohm resistor will have only the 10 amperes of current flowing through. Is not so, uh, because the current in the 10 ohm resistance now it is assumed in this direction, but we don't know the actual direction, because the direction of the current will depend upon the total sources and its direction, that final cumulative source and its direction. Okay, so in that case it is necessary to use the superposition theorem, so that it will be helpful for to find the final value. So in order to do that, we are going to find the current in this resistance in 3, because this problem will take quite a bigger time to solve depending upon the size of the network. So for the first, so I would say that I will consider this circuit into two different forms. In each form we will be using only one source at a time. So let me calculate. Let me take this. So this is the first network. Let us take this as the first network. In this first network, we will solve. That is, we will ignore the other circuits. So ignoring other circuit means like we are making zero. That is, the circuit is voltage sources will be made zero. So here we have given with a voltage source for this. So if the voltage source is given, we will short circuit it. So that is the first condition. You can see the next source here, which is a current source. So we will open circuit it. So I'll keep something like this. Okay. we will consider open circuited. So the circuit given here is this. So in the superposition theorem, it is necessary to consider these circuits. That is, first thing what we have to know is we should know the number of sources given to you. So here it is very clear that there are three sources given to you. One is the voltage source, which is of 100 volt. Another voltage source is of 50 volt, and the another source is of current source, which is a current source of 10 amperes. So the two voltage source and one current source is given to you. So whenever I solve this problem, now I will have three different circuit. In each circuit we will have only one source at a time. It means I will zero the other sources. Okay, hope you should remember in the previous lecture I told you how to make the sources zero. I will just repeat it again if you are not could remember it. So in order to make the sources zero, we have two things, because since we have two sources, one is the voltage source and the current sources. In order to take and to make voltage source zero, we have to short circuit it, and to make current source zero, we need to open circuit it. So we are going to follow this same condition in order to, so the above given circuit can be replaced or can be given in terms of superposition theorem in the in this following. Let me copy the, so I copied this circuit. So this circuit can be drawn in this way. So let me consider this as the first way of solving. So I will keep my first source of 100 volt as same, and I will remove the other sources. In this case, my this source, the last source is an voltage source, so that I will short circuit it, and this is a current source which is given here. So in this case I will remove my current source, and I will open circuit it. This is how I would open circuit it. So this 10 amperes is open circuited, so I will remove this value. Okay, so this is how the first circuit will. So for this circuit I need to find the current. I don't know the actual direction for, but for this circuit the direction would be slightly changed. That is, this is the direction of the current, which is I. I'll take it as IL dash for the first one. I'm going to find the current of this. How can I find? But before going to the problem, please understand that this 7 ohm resistance is open circuited. So obviously there will not be any current flowing through this. There will not be a current flowing through this. So even when we are finding the equivalent circuit, equivalent R resistance, that is a resistance value, equivalent resistance, we will not be able to consider the 7 ohm resistance, because this 7 ohm resistance is just open circuited. So it is better to forget about this 7 ohm resistance. We will remove this, right? So the circuit is as simple as this. Okay, now eventually by this problem which is considered, there will be a current coming out of this. Let this be the main current which is coming out of it, which flows through the 5 ohm resistor. At this point it will get split up into this one and this one, and this is the current, that is current flowing through this will be same as this current flowing through this 10 ohm resistance. So, and let this be the other current, we will just name it as I1 for a time being. And now we need to find what is IL dash. So to find IL dash, we can use a simple method. Just think about it, you are not going to find the branch current. In order to find the branch current, it is very essentially noted that in order to find the branch current, you need to know the current division rule. The first foremost thing you need is to current division rule. Current division rule. So by current division rule, what is IL dash? IL dash is equal to the opposite resistance this by divided by the sum of the resistance in this branch. So the opposite resistance is nothing but this 15 ohm resistance. So it is nothing but the 15 ohm resistance divided by the sum of the resistance, that is 15 ohm resistance, plus the sum of the resistance in that branch, so which is nothing but 3 plus 5 plus 10, 3 plus 5 plus 10. So this is the sum of the resistance into the actual current which is being splitted at this point, at this node. Okay, so it is nothing but the actual current which is getting splitted. So in this case, if I am able to find the capital I, that is a main current, then I will be able to find IL dash. So here the main current is given as, sorry, this is not IL, this is just I. So in order to find I, we should know the voltage divided by the equal resistance. The voltage value is 100 volt, I know that, but we need to find the equivalent resistance. In order to find the equivalent resistance, we will be solving it together. So it is known that this 5 ohm, 10 ohm and 3 ohm all are in series. These all resistance are in series, right? So that in turn it is in parallel to this 15 ohm resistance, right? This is in turn parallel to, finally those combinations are in series with this 5 ohm resistance. So the equivalent resistance formula can be given as, R equivalent is given as the combination of 5 3 5 and 10, which is nothing but 15 18. So 18 is parallel to 15 ohm resistance, and then it is in series with 5 ohm resistance. So the actual formula is 18 into 15 divided by 18 plus 15 plus 5, right? Let's see what we get here. We get it as 13.18 ohms. So this is the equivalent resistance what get, through which now we are able to find the value 100 divided by 13.18 ohm, which is 7.58 amperes. Sorry, this is not IL again, it is just I. So the main current is found as 507. Now let us substitute in the actual equation to find the value of the IL dash. So IL dash is equal to the resistance 15 divided by 15 plus 18. So it is 15 plus 18 in the denominator, which is nothing but 33. So it is 15 divided by 33. You will get it as 0.45. Okay, 15 divided by 33, you will get as 0.454, 0.454 into, now the value 7.58. So we get it as 3.44. 3.44 ampere is the current through the 10 ohm resistor, considering only one source. So that you have to remember, right? So this is the first circuit what we found. Okay, now we will solve the second circuit. So what I do is, like, I'll send this bottom. Okay, I'll use this, I'll keep this. Okay, now we have the next circuit to be drawn for this at this point. So let me copy this. So for the next circuit, we must consider only the second source and not the other two sources. So I will remove this 100 ohm, sorry, 100 voltage short circuited because it is a voltage source, and here also I can show short circuit the because it is also a voltage source. Okay, now I'm going to consider this circuit only with the 10 amperes current which is entering into it, right? So here also the current direction will slightly change because we understand that the direction from the currents will be also something like this. We will take this IL double dash. Okay, IL double dash. So here this circuit can be redesigned, because in order to find here also we can use the current division rule in the redesigned in a simple way, that we have a resistor here and a current source which is of 10 amperes, and this is 7. So there are two networks is going on. One, at from this point the current will be divided, that is the current which is coming out of this will be divided into two. So one which goes here, we have taken it as IL double dash, and let me take it as this as I2 or something, some other current which is going. We are not bothered about how much value of current is going, but instead if I have to find the equivalent value in that is if you want to find the current which is going here. So here what I have given here, what is there is a 3 ohm resistance, after which it splits to 5 and 15. Okay, and here I have a 5 ohm resistance and a 10 ohm resistance, 5 ohm and a 10 ohm resistance. Now by the current division rule, in order to find the value of IL double dash, it is nothing but the opposite resistance divided by the sum of the resistance. So here the opposite resistance is something 3 ohm resistance divided by this. So it is very simple. It is very simple. And the which is the main current here which is splitting, which is the 10 amperes. So we have no bigger calculation here. So we can directly write it. So IL double dash is equal to opposite resistance is 3 ohm resistance divided by the sum of the other resistance, which is nothing but the 5 ohm and the 10 ohm. So it comes to 15 ohms resistance. Okay, I'll write it simply, simple words. The 3 divided by the sum of the resistance, which is 15, into the current, the main current which is getting splitted, which is nothing but 10. So for which let us now see, it is 3 by 15 is nothing but 3 divided by 15 will give you as 0.2, and in that is 0.2 into 10, which is nothing but 2 amperes. So this is the very simple now. This is we can 5 double dash gives you 2 amperes, right? 2 amperes is given. So now we have found the current because of the two resources separately. With the last left one is the other one. So we'll add up this and we will find the next one. We'll again, I'll copy this, I'll bring it to the next slide. Okay, now here the 50 ohm is considered, 50 volt is considered. We will remove all the other sources. Okay, I'll short circuit this, and here, as I told you before, this 10 amperes is a current source that will be open circuited because it is a current source. So if I open circuit it, it means that this 7 ohm resistor will not get any current. So it is same as not being in this. So 7 ohm resistor is not required. Okay, this is the circuit now. Now this IL, let us take it as IL triple dash, and this direction is correct because the 50 volt supply will give a current, something like this. So now we need to find a circuit which comes, this is nothing but the current, this IL triple dash is nothing but the total current that comes out of the 50 volt supply here. So the total current can be obtained as, that is we can say that is IL triple dash is nothing but the total current, which can be given by Ohm's law. It is the total voltage divided by the equivalent resistance. So the total voltage is known as 50 volt, and now the equivalent resistance can be found from solving it from the left side. So we can see that the 5 and 15 are in parallel. That again goes in series with the combinations of all these things, right? They are in series with the combination of all those things. So the R equivalent can be given as 5 parallel to 15, and that is in series with 3, 5 and 10. So 5 parallel to 15 plus 18. So let us see what is the R equivalent value. What is now we have to find what is 5 parallel to 15. So 5 into 15 divided by 5 plus 15, which is 20. We get it at 3.75. 3.75 we add it to with 18, we get 21.75. 21.75 ohms. This is the equivalent resistance. Now we can substitute here, that is 50 divided by 21.75. So what is that? 50 divided by 21.75. We get it as 2.298. So almost approximately equal to 3. 2.298, or we can approximate to 2.3 amperes. So IL triple dash is equal to 2.3 amperes, right? In this 3 circuits, now we have to add it, but see the direction of the current actually it is. So in the first case, the direction of the current in the 10 ohm resistance is from top to bottom, right? From top to bottom like this. In the second case also, we obtained the current in the positive considering the direction from again top to bottom. But in the third one, the last one, we see the current which is going in the opposite direction. So we will add the first two currents. So therefore the total, I'll write it as, therefore the total current in 10 ohm resistor considering all 3 sources is given as, what is it? IL dash plus IL double dash minus IL triple dash. The reason why I put a minus here is because the direction of the current in the third circuit is actually opposite to the currents in considered in the all the other things, because you can see this current IL triple dash is going from bottom to top, but in the other case it is from top to bottom and top to, so the same directions will be added and the different direction will be subtracted. So let us now see which is 2 amperes, 2.3, and then sorry, the first one is 3.44, 2 and 2.3. So we will write it as the value 3.44 plus 2 plus 2 point, sorry, it's not plus, again consider it as minus 2.3. So add this, you get 5.44 minus 2.3. So let us see exactly what is the value we are getting. We have 5.44 minus 2.3, which we get at 3.14. So 3.14 ampere is the actual current, load current, which is going in the load resistance 10 ohm. Okay, considering all the 3 together. So this is how you can easily solve it. The reason why we are solving this using the superposition theorem is, when we try to solve this circuit using the Kirchhoff's voltage law or Kirchhoff's current law separately, it's again going to be complex. Or we have the method of some mesh analysis. If I take a mesh analysis, I am given with the voltage source and also current sources, so it is for me difficult to consider the current source in case of mesh analysis. And I cannot change this source to a voltage source, because we don't have any parallel resistance connected to the source exactly, so that's the reason. And similarly, we will not be able to either what we have to do is we need to convert all the sources into the voltage sources to the current sources, then finally apply the nodal analysis. That can also be done. So there are some complexity in finding out the actual current values and so on in case of different differences. So in nodal analysis, what we do is we will be converting this totally to a voltage source. I mean, from this voltage source to current source will be considered considering these elements, and for this we will consider this two as the conversion for source transformation to a current source. Then we will consider this as a node 1 and node 2. We will find the node voltages as VA and VB, and then after finding the node voltage VB, we will have to find the current in this. So that is voltage divided by resistance, that is VB. We will get VB divided by 7 will give the current in this resistance. This is how we will be finding it. So that is one other method, but this superposition theorem will end up in this kind of this is very simple to find. That is, we will ignore all the other sources, keeping only one active and finding it. So this you can use it to find the actual value. Okay, this is the method of solving superposition theorem.